back to Software Engineering 2FA3, Discrete Mathematics with Applications 2. I am Bill Farmer. We're going to continue on the topic of Turing machines and computability, and today we're going to begin by talking about undecidable decision problems. Now, I want to go back to something we talked about last time. If you remember, I said that the distinguishing characteristic of a modern computer was that it can store and run programs. So an obvious question is, can a Turing machine run and store programs? Well, certain Turing machines can. These are called universal Turing machines. So the way they work is we fix an encoding scheme over 0 and 1 for Turing machines. And the way this works is each Turing machine is represented by a string, S sub m, of zeros and ones. And each input string for my Turing machine M is represented by a string SMX of zeros and ones. So we have a way of encoding every machine, and for each machine we have a way of encoding the input strings. And then we can construct a Turing machine U for universal, such that U accepts this string. So this represents a Turing machine. This represents an input to a Turing machine, and there's a special symbol to separate the two. And if it accepts this, it will accept this if M accepts X, and it will accept this string if M rejects X. And it will loop on this string if M loops an X. So in other words, it's going to be simulating X. And then it will also reject any string where Y is not a valid encoding of a Turing machine. And if Y is a valid encoding of a Turing machine, Z is not a valid encoding of a string for that Turing machine. So U can simulate any Turing machine. So this is pretty cool. We have one Turing machine that can simulate every other Turing machine. Now, as I said, U is called a universal Turing machine, and the language it accepts is the language of SM # SMX. And it accepts this for every X in L of M. So basically, it's going to accept a string like this if there is a Turing machine M, and that M accepts X. Okay. So we have these universal Turing machines. We'll come back to them later. But now we're going to talk about an important proof. This proof was done by, or theorem was proved by Georg Cantor in 1891. What he proved was that there does not exist a bijection from the natural numbers to the power set of the natural numbers. The power set of the natural numbers is a set of all subsets of the natural numbers. So remember, a bijection is going to be a function that's total, it's going to be injective and surjective. And it establishes a one-to-one correspondence between the natural numbers and the power set of the natural numbers. In other words, shows that the cardinality, or the size, of these two sets is the same. So Cantor showed that there is no such bijection. And another way of saying it is that means there is an uncountable set. There's a set whose members we can't count out. It's too big to be counted out. So it's a set bigger than the natural numbers because, of course, we can count out the natural numbers. We have 0, 1, 2, 3, and 4. Okay, so this is an extremely important theorem. And the theorem was proved by Cantor using diagonalization. And diagonalization is a very important proof technique. Many of the major results of the theory of computing use diagonalization. So I'm going to show you the proof right now. So we're going to start by assuming f exists, assuming there really is a bijection from the natural numbers to the power set of n. So if there is such an f, then we can basically count out the members of the power set of n. So f of 0 will give us the first member, f of 1 will give us the second member, f of 2 will give us the third member, and every member will eventually appear on this list. And remember, every member is going to be a subset of the natural numbers. So here are the natural numbers, and let's say if we look at f of 0, the first set, if 0 is a member, there will be a 1 here. If it's not a member, it would be a 0. So we can see 1 is a member of the set, 3 is a member of the set, and 1, 2, and 4, and 5 are not members of the set. So this string of zeros and ones at each line tells us what are the members in this set. So we have an infinite two-dimensional matrix, and it tells us what's in all the sets in the power set of the natural numbers, because we're assuming that there's a bijection from the natural numbers to every member of the power set. So we have this big infinite two-dimensional matrix. Now what we're going to do is we're going to construct a set. I'm going to call it D for diagonal. And it's going to be a sequence, just like we can think of these sets as sequences of zeros and ones. It's going to be a sequence of zeros and ones, sequence of bits, zeros and ones. And here's how I'm going to define them. I'm going to define the mth bit as being 0 if m is a member of the mth set for this function m. And it's going to be 1 if m is not a member of the mth set. So what this does is I have D, what it does is present an obvious question. Where is D in this set, this counting out, this sequence? Where is D? So let's say we think D might be here. If D's here, then we know that, according to this, 2 is not in the set D, if D's here. But what does B2 say? B2 says that this is 0 if 2 is a member of B2, and it's 1 if 2 is not a member of B2. Well, we know right here that 2 is not a member of B2, therefore 2 is not a member of F2, therefore B2 will be 1. So for D, B2 is 1, but for F2, it's 0. So D cannot be this. And if we look, could D be this? No, it can't be this because it's going to differ here. It's going to differ on the diagonal of all these sets. D cannot possibly be any member of this sequence. So every member of the power set of n must be, by assumption, a member of this sequence, and now we've constructed one that's not. Therefore, we can assume that this is not true. D does not, or F does not exist. So f of n does not equal D for all n, and this is a contradiction. Therefore, there does not exist a bijection, and we know this set is going to be uncountable. We know it's bigger than n. Okay, so this is an extremely important result. It shows that there are uncountable sets. It also shows that there are sets that have bigger cardinality than n, and if we take the power set of n, that will have cardinality greater than the power set of n. So we actually have an infinite number of cardinalities, an infinite number of infinite cardinalities. Okay, so this is very useful for what we're looking at, because with this result we can show that there exists an undecidable decision problem. That means there's going to be some decision problem that's undecidable. So how does this proof work? Okay, so consider the decision problem of determining the membership of whether a set is in the power set of A. So we have a set of natural numbers. We have some set of sets of natural numbers, and we know by theorem 3 the power set of n is uncountable, so there's going to be an uncountable number of decision problems. We're going to get a different decision problem for every one of these sets. So when we have one of the sets, the decision problem is a natural number a member of this set A? So we have an uncountable number of such sets, so we have an uncountable number of decision problems. However, there's only a countable number of Turing machines, since, as we showed, every Turing machine can be encoded by a string over zeros and ones. And there's only a countable number of these strings. So we have a countable number of Turing machines. We have an uncountable number of decision problems. And therefore, by the Church-Turing thesis, there are going to be not enough algorithms to compute every decision problem. The Church-Turing thesis says that we can represent all algorithms using Turing machines or any other Turing-complete model of computation. So to repeat, there's not enough algorithms to compute every decision problem. There's a countable number of algorithms, but an uncountable number of decision problems. So there must exist undecidable decision problems, problems that cannot be computed by an algorithm, problems for which there is no algorithm to compute them. And the thing to notice about this proof is that it's non-constructive. It shows there must exist an undecidable decision problem, but it doesn't give us an example of one. And this brings up an obvious question. What is an example of an undecidable decision problem? So this will be the topic for our next lecture. We will look at a specific undecidable problem, the halting problem. Okay, we'll stop here.